we're at this point where I actually got something to work in CoppeliaSim. It's sometimes hard to get these legged machines going. So this is like the simplest version of what I think will work in CoppeliaSim, which is the passive walker. And the model I've shown here on the screen. And we basically we make a planar robot by putting a spherical joint, same thing which we did for rimless wheel. We rotate gravity, same thing we did for the rimless wheel. Now here it's slightly different here in terms of joints, which is we have two ankle joints, and you can see them here. And these ankle joints are only made so that the foot can clear the ground. In Matlab, when we did this, we actually ignored the ground scuffing, but here you cannot. Now there are ways to do that too. You can turn the ground detection off and on, and that's more complicated, I figured out. So it's just better to put an ankle joint. And then the hip joint as a spring. Now in a passive robot, which I showed you, there was no spring. In this case, you need a spring because I couldn't get it working without a spring. Now you could potentially get it working without a spring if you change the slope, like we have done for the Matlab code. But in this case, I'm going to show you sort of a more faster gate by putting a spring and putting a bigger slope. There are no springs in CoppeliaSim, so you need to put the springs yourself using torque, set torque. And I'm going to show how to use finite state machine for control. Now, when I say control, really it is basically the control for the ankle joints, right? The ankle joints have to be moving up and down so that you can do foot clearance. So here is the demo of what I got to work. Okay, so there it is. And this is at real-time speed as per CoppeliaSim. And then you can also see the steps. It's printing the steps as the robot goes in circles. And zoom in, and I'll provide this too. This was like the code which I wrote offline, but I'll try to reproduce this code online and perhaps show you how to do this in a logical fashion rather than just copy pasting a big chunk of code. I will copy paste code though, otherwise it'll take us forever to do this. And the code which I'm going to copy paste is essentially the rimless wheel code, which we've already debugged and explained to you slowly. Okay, so that's one circle and just keeps going, it doesn't fall down. The key thing here is that actually I have the simulation speed to set as 10 ms. If you actually change it to 50, it doesn't work. Yeah, it fell down. You can try 25. That doesn't look like real time, but yeah, it's really hurrying down. That's because it's not real time somehow. That seems like it's working. So the reason why it's very sensitive to simulation time is because, well, there's a spring there. And once you have a spring, then the simulation time does matter. So here it looks like it's okay, it's working fine. Okay, so I'll stop here, but I recommend going for the most accurate simulation you can. The way this will go is, let me see. So before I get into the modeling, there will be three parts to this. There is the modeling, okay? There will be the sensing. So I need to sense few things like absolute angle of the legs, the position of the foot, and then the actuation code, which is through a state machine. Now, when it comes to the model, the way I'm going to do this is I'm going to make the two legs to be cylinders, and I'll put a center of mass somewhere halfway, mass of 1 kg. The feet would be spheres, and they would have a mass of 0.2. So they are 5 times less massive than the leg. Okay. The hip joint is a revolute joint, where I need to put the spring through a torque at the hip joint. The ankles are prismatic, and I'll actually use a position control there. And then to restrict motion in 2D, I'm going to use a spherical joint, as I've done in 2D motion. Okay, so let's start with modeling. That's the first piece. What I'm going to do is, in addition to, well, for the modeling, I don't need it, but I will actually use some part of the code I developed for this rimless wheel, which I use to set gravity, basically, right? And then I also get the absolute angle of the torso. I'll use some part of this code later on. Okay, so I'll just keep that handy. So let us make a new scene, and let's save it first. File, save scene. Let's call it pipette passive class. Okay, so I'm going to start from the base, the stand, the spherical joint, then go to the biped. So let's do that. Add primitive shape, cuboid, and then you can choose whatever you want, 0.05, 0.05, 0.05, and this is inconsequential really. So that's at 0, 0, 0. Let me call that, let's call it stand. And let's make that, first of all, static, right? We don't want that to move. So not respondable, static. Okay, now let's put a spherical joint right on the stand. Let's blow it up so it looks big. 0.2 maybe, that's too big. 0.1 maybe, okay, that's fine. Okay, and really, as I've told earlier, the longer you make the boom, the more it is like a planar motion. So you won't have a big boom. Now this floor is 5 by 5, I think it's very small. So you can actually increase the size of the floor by clicking on the floor and then maxing it out. So max it 25. You could actually go to 100 also. There are floors that are available. Okay, so now one thing to remember here is if you click that and close it, that icon, that GUI is never coming back. So never close this like this. Don't quit it. Just click somewhere else, it will go away. Okay. If you click that and then you want to resize, then you will not be able to do it. You'll have to delete that floor, introduce a new floor. Okay, so now we have this. Now what I'm going to do is I'm going to set up, that's how it looks. I'm going to set up the boom, well, the robot right on the y-axis, so way down here. So this is, I think, so 25 by 25. So this is 12.5. So I'm going to set somewhere at 10. Okay, and so the way I'll start is I'll start from bottom up. I will start with the foot, because the foot is on the floor. Go to the ankle joint, leg, hinge. So once I have one leg, I can just copy paste it, and then I just need the hinge joint. So let me start with the foot. So primitive shape, sphere, and these are numbers I just cooked up earlier. Makes it easier if you have these numbers ahead of time. Sphere, okay, and let's call that foot 1. And let's just move it all the way on the y-axis. So world frame position. Let's just move it all the way. So z is basically the height of the center of the sphere from the ground. That's 0.05 because it's half of 0.5. But we want the y coordinate here to be 10. And there it goes. And so let's just follow that. Let's just go there. Okay, there it is. Okay, so now I'm going to use this as a basis to really build this leg from foot all the way to the hinge joint. So let's just create the ankle. That's a prismatic joint. So let me call that ankle 1. And it's basically sitting at 0, 0. And the fastest way of moving things I found is just to make that as the child, go to position, go to parent frame, just make it 0, 0, and then it just appears there. It's much easier than guessing the distance. And then you can just remove it from being the parent. Okay, so now what I'm going to do is I want that ankle joint to be between point. So when it needs to basically retract and protract to do ground clearance. So what I'm going to do is I'm going to actually remove this first. I'm going to move it slightly up. Let's say I move it to not the y, but the z coordinate, 0.2. And actually, I have some dimensions I want to set before I move on. So let's just set this to what I want them to be. I want this length to be 0.2. and then that the other one to be 0.05, just to coincide with the dimensions of the foot. 0.2 and I just said 0.02 is fine. I guess this is the diameter of the inner. So I guess if I make it too big, it will look very weird. So you can try it. Just looks very weird. So I just put 0.02. This is fine. Okay, 0.2 and point. Okay, so we got that. Now what I want to do is I want to ensure that the minimum length is 0, and the range I want it to be 0.2. So that's like the length at which it's maximally stretched. And then if it is fully stretched, it will look like that. And if it is fully unstretched or protracted, it look like this. And that looks like just the opposite of what I want it to be. So I'm going to rotate this joint by 90 degrees about the x-axis. So let's just rotate orientation about the x-axis, sorry, 180 degrees about the x-axis or y-axis, whatever, 180. I didn't change anything. I think it should be about. By the way, that should have worked. I couldn't see it because I had the leg retracted. So both of them should have worked. I should have actually changed this first to show you how it's saying. Okay, that looks fine. It's not clear to me what's going on here. So what I'm going to do is make the foot as the child of the ankle. And now let's do what 0. There it is, 0.2. It just seems very weird that this thing is going inside. So I'm going to just move the ankle joint up. But then if it's a parent of foot, it will break the foot along. So I'm isolating both of them, going to ankles. Let's just move it to 6.3. Okay. Now let's just do child. I'll go to ankle. So 0 is this. And 0.2 is this. If it bothers you, you can actually move it a little bit up. Technically, it doesn't really, there's no real collision or anything between the two. So you don't have to worry about joint and an object. But if you like, we can just move it slightly up. Now 0.35, and that is to coincide with the 0.5 is because of the diameter of the sphere. If that helps. Okay, so again, what happened was I did a mistake. I shouldn't have made that a child and everything moved. Go back, isolate this, move it up, 0.35. And now we can make this as a child and then see what's going on. 0. That looks fine. 0.2. Okay, so this looks fine. Okay, now let's introduce the leg, primitive shape, cylinder. Yeah, and I'm going to just go with 0.05 for the diameter to coincide with the diameter of the sphere. And the length is going to be 0.8. That's because I want to make 0.8 plus 0.2, which is going to be 1 meter for the leg length. That includes the ankle joint too. So 0.8. Okay, now that's again at the origin. Fastest way to move it, leg 1, is to make it a child of maybe ankle or foot. Then go there and say you want this to be 0, 0, 0. Okay, so that's buried there. You want to move it up, and the distance you want to move it up is going to be, well, let's just go to world frame now because that's easier. So it's 0.2 meters for the ankle and 0.4 meters is where the center of mass is going to be. So 0.4 plus 0.2 is 0.6. I think that if you give 0.6 for Z, it should just be, it should be. Okay, that looks fine to me. Let's see what's going on. Let's just make that as I remove the leg out, make the ankle as a part of the leg, which is how we will eventually have it, and then foot is part of ankle. So now let's, if we go here and say, go to the ankle properties and say 0, it just goes inside and 0.2. So that's not good. Let me just move that leg a little bit up. So I think I need to move it at least 0.65 just to make it equal to, So the sphere, the 0.05 is due to the diameter of the sphere. Okay, so that was a problem because everything moved up. It's not a good idea. 0.6. I need to isolate that. Let's remove that. Make the go there and then make it 0.65. Okay, let's see if that helps. Not this, but okay, that looks like it's barely possible. In fact, I will never actually go and make it collide with that. I'll actually go retract up to 0.05. So that's how it will look when it's retracted, and then 0.2 when it's fully in stance. So this is good enough. I don't need to modify anything. Okay, I want to change some of the properties. Before that, let me just make this as the child of leg. I'm going to make this mass as 1 kilogram. Okay, and note that the center of mass of this is 0.4 from the hip. And then let's go to foot and then just make its mass point. Okay, now you can change the inertia, not for this, the leg, but here it's inconsequential. It's not going to affect us much. You could, in fact, change the inertia and that would change the spring constant, but I did not investigate those things. Okay, so we have the leg all set. Now let's just, first of all, let's put I shouldn't be doing this. Let's see where this foot is. Anything you change is going to affect, yeah, there it is, it's affected. Not good. Let's see, I just, if you don't put it in the right way, then when you do the control, it's just very nasty. So I recommend not moving it. The Z coordinate doesn't look good to me. The foot is in the world frame. It's okay. So I need to, okay. So here's the thing. I highly recommend that you should ensure that the foot is in contact with the ground. This is just like a robot is. If it's not on the ground, then it's going to behave very weirdly when you actually start the controller. So there's some assumptions we make. So what I'm going to do is, it's unfortunate, but I'm just going to go with this. I'm just going to go back and make it proper because I don't think there's any value in going forward unless we fix this. So let's get the foot position. We want the y coordinate, as I said, it should be 10. The z coordinate should be exactly the what do you call, the 0.025, which is half the diameter, and the x coordinate should be 0. Okay, x, that looks right. Okay, now we just make this the ankle as the child of foot. Go there, parent frame, 0, 0, and then this should be, it's supposed to put 0. And now let's move it up 0.3. I think that it was 0.3. And then let's make the leg as child of the foot, just because I want to set the x and y. And then the z coordinate, let's go as with the world frame, and then move it. If I'm not mistaken, we put it at 0.625. Okay, I think I'm back to where I was. Ankle is sort of, and then foot is part of ankle. And so if we go here, put 0. I'll go up to 0.05. So it should be good. You can modify, but I think this is good enough. So let's just make it 0.2. And now we just, one sanity check is to just ensure that the foot is exactly 0.025. That's very important. Okay, so we got this going. Let's add a joint, and that would be a revolute joint. And let's call that revolute joint as a hip. And the way I want to place it is, I want to place it right here. And so first thing I do is I just make it a child of leg. Then go to translation, parent frame. Let's make it 0, 0. So it comes right in the middle, but that is should be 0.4 because the length of this leg is 0.8. So 0.4, get it up. Now I can see that it's not quite the way it should be. I need to rotate it about the x-axis. So let's rotate about the x-axis. So by 90 degrees. It looks good. I would just want to make it slightly bigger so it looks reasonable. So the length is 0.15 is fine. The thickness I wanted to coincide with the sphere radius, so 0 or foot radius, so 0.5. Okay, and now I need to move it by half of 0.15 to the right. In this case, it will be along the y-axis. So assuming still keeping that as the child of the leg, what I'll do is I'll go to position, parent frame. I think this will work. Let's see, 0.075 if everything looks right. Okay, there it is. So I got the hip joint. Now I need to create another, let's remove this from this chain. Now I'm going to create another leg, and that's so simple. Just copy all this, paste it. And this leg now, let's go rotate this, has to go right here. So what I can do now is, it's actually simple. We just translation and then along the X. Okay. The easier way to do it is probably go to make it a child of hip, and now go to translate. And then now you see it's 0.75 on the left. I just needed to make it minus 0.75. I think it'll work. That's it. Okay, now we got that. Okay, so now we've got the legs. We've put the hinge joint. We only need to connect it to the spherical joint. So what I do is now, and this is kind of important, the leg will become a part of the spherical joint. So the world is connected to the leg one, which is this leg. That leg is connected to the ankle and the foot. Okay, so they move back and forth. Now the hip joint has to connect to the leg, and then the ankle, the leg two connects to the hip joint. So I just need to take this and drag it and drop it over here. And so this is basically the assembly I'm looking at. Okay, now if I run this, it will fall, and this is good because it's falling in a very symmetric way. If I don't want it to fall, which is what I will be doing here, is I'm going to go and turn off gravity. And so that's right in this. So now it will not fall. Okay. Now let's just see what the angles look like. So, so you really play with it. So we've played with the ankle joints, right? So 0.2 is this, 0.05 is retracted. Let's play with the hip joint. So if you look at the hip joint, and if you set it to 25 degrees, you can see the leg is tilting forward. And then if you put it minus 25 degrees, it'll tilt backwards. Okay. So my goal is to start the robot in this position with the hip, basically I'll start it such that there is a torque which holds the hip in this position, 25 degrees, till that foot hits the ground. And once it hits the ground, and then I will just switch on my passive walker, which is basically there'll be a hip spring, and that will just take care of swinging the legs. And then I have to also take care of the ankles. So this is basically sort of the end of the first part, modeling. Got this? If you look at it from far, it's connected to the spherical joint. Okay. Okay, so next part. Okay, so for the next part, I'm going to, as I said, look at some of the code I wrote for the rimless wheel with torso. I'm going to add a frame, a moving frame, and this will basically help me to keep track of two things. One is, by frame, I mean I'm basically going to make a dummy over here, which is basically going to move on the ground, but it will be exactly below the hinge or the hip joint. And that will basically help me to keep track of the angle of the boom makes with the x-axis or y-axis, whatever you like. In this case, it's going to be about the x-axis. And once I know that yaw angle, I can use that to set gravity. Okay, the gravity will set that. So normally gravity points downwards. It's just g. But when this thing is moving in circles, we want to set gravity such that the gravity in the forward direction is g sine of slope, and the vertical component is g cosine of slope. The vertical component is not a problem. The horizontal component, the issue is that this gravity is basically going to be applied in the direction which is always in the forward direction. But as the robot moves in a circle, that forward direction keeps changing. So sometimes, for example, it will be along the x-axis, then it will be at an angle to the x-axis, then it will be at the y-axis. So when the robot reaches on an finite x component and y equals 0 and so on. So that's why I need to keep track of the yaw angle and use that to set gravity. And then I'll also find the absolute leg angles. So the angle made by the leg with the vertical, and that will be useful if I want to get the ankles to retract and protract. And then I will also keep track of the foot position, which is this position. So if the foot is, say, 0.025 from the ground, that means the center is 0.025. That means that that foot has hit the ground, and I can then switch legs. The convention I'm going to use is that positive absolute angle is when the leg is on the left side of the vertical, and it's negative on the right side of the vertical. The easiest way to remember this is that when it is to left side of the vertical, it is in the counterclockwise direction, it's a positive angle, and when it's in the forward direction, it's negative because it's clockwise. Okay, so that I need to start working on this, but before that, I need to attach this object. Let me just attach that object first. So first, I will add a dummy, and I'll call that literally a frame, because that helps me to keep the frame with respect to the x-axis or y-axis. So let's just make it slightly bigger. Point to zoom here. Right now, it's basically at the origin, so I'm going to get it right below the hip, right in between the legs. So what I do is I'll make that a child of hip, and then I just first set it to 0, 0, 0. Now it's up. All I need to do now is to move it such that its z coordinate in the world frame is 0, right? So go world, and I just set the world coordinate to 0. So it should be right there down. Okay, so that apparently is below that. I think I just make it slightly bigger. Make it 0.5. Is that big enough? Okay, that looks reasonable. Okay, so this shouldn't be the child of anything. Just keep it outside. Okay, so that's the only modification. So now let's just start adding a script. New script is going to be a non-threaded script. And this bug, I have to close this first before I can actually associate it with something. So just so you can associate it with anything. I'm just going to associate with say stand. Okay, the script is ready. I just need to start populating it. Now, first thing I'm going to do, as I said, I'm going to work on sensing. Okay, I'm going to set gravity, get the yaw angle, set gravity, get the absolute position of the stance leg and swing leg, or in this case, leg 1, leg 2, and then also get the foot position. So there's 4 things I'm going to do. So first 2 things, yaw angle and the gravity rotation, is going to be taken from my rimless code, which I developed some time back. So it's basically taking this stand, torso, and frames. I need a few things. Let me just copy this whole thing and then eliminate what I don't need. So go to class. Paste it. Okay, so let's see what I need. So I do have a stand. I don't have a torso. Let's get rid of this. I don't have a rimless tape, no motor. So those are 2 things I need. This. In this case, I decided I'm going to go with a slope of, let me see, I think it's 0.1. Okay, and then I'm going to go, this basically keeps track of which direction it's going. In this case, it's going to go clockwise direction, as you saw. And then I need to write these 2 functions, which is get the yaw angle and then set gravity. So I'm going to copy this from my code. Okay, so there is a video on how these angles are set, or working through this slowly to get these angles. So you can watch that video to see how and why this code is the way it is. Just go to this and paste it right here. So let's see what's going on here. So I'm getting the position of the stand, get the position of, okay, the torso. So I needed the torso position, which is, let's see what it is. I needed the torso position. So the torso is right here in order to basically keep this below the torso. Now that role is performed by the hip joint here. So I'm going to get the object for the hip joint. So hip equals hip. And as I said, this role is performed by the hip. Okay, so what I do here is I get the X position between the distance from the base, that is the mid part, the stationary part, or the starting of the boom, and then the body, or in this case, it's the hip joint, the X and Y, and then I find the yaw, which is basically the tan inverse of dy dx. A tan 2 gives me the right angle for a 360 degrees rotation. So that gives me the yaw angle. Okay, so for example, if it's along the x-axis, the angle will be 0. When it's along the y-axis, the angle would be either 180, 90, or minus 190, or minus 90. So then once I get the yaw angle, I can set gravity. This is not what I wanted. Let me close this. Let me get the code for set gravity. Set gravity. Space that. Okay, what this does is basically it sets the gravity in the y direction, z direction, which is gravity times the cosine of slope. But then the x and y direction are set basically based on not only the slope, but also the yaw angle. Okay, and that's why I need the yaw angle. Once I do this, and then there's, of course, there's this direction thing, which is basically you need to set the direction always in the forward direction in which it is moving. And that direction basically takes care of this. So this basically sets the gravity in the x, y, z direction. So now we can actually run this and see what goes on. So it falls down. Okay, can actually do real time and make it fall. Okay, so that looks good as we expected. Now I have to do two more things here. One is get the absolute angle of the leg, because it'll be useful later on. And I can actually look at some code here, which I developed to get the angle of the torso with respect to the vertical. That's pretty much what I need. So I'm going to go to the code here and get the torso pitch angle. So just get that, paste it inside here. Okay, so let's just call it something else. Let's call it, let's say, get absolute angles. Okay, so in this case, I need to get the absolute angle of the legs. So leg 1 and leg 2. So before I do that, let's see what's going on here. So first, this is in respect to the other code. So I was getting the torso position. I was getting the moving frame. Okay. So, sorry, I was setting the position of the frame. In fact, the way I did this was I was setting this point, the moving frame, to be exactly below the hinge joint as it keeps moving. And once I know that, then I can find the angle with respect to that. So as I said, the thing which is performing the role of a torso is actually the hip joint here. So I'm going to change this to hip. And then this is going to be hip. So this is setting the X, Y, and the Z position is always 0, because always is going to be on the ground. Then I set the orientation of the frame. So this is basically setting it to be the angle made by the torso with respect to the x-axis of the world x-axis. Okay, and then I get the Euler angles for the, in that case, it was the torso with respect to the frame. In this case, I want it to be the legs with respect to frame. So I need to do this for leg one. So let's call that Euler angles leg one, and then Euler angle leg two. And then I need, as we've seen earlier, we need to get the Euler angles, the first angle from that. So this here, and we can actually return two values. So the first component is actually the angle we're seeking. Okay, so now there's going to be a problem here. Leg one has not been defined as an object. So let's go here, define leg one. One, and then just copy that. Okay, let's just make it print this value. So you can just call that here just to check, and then say print. Okay, so it returns two things. So it returns Euler angle one and Euler angle two. So let's call those. See what name I use in my notes. Okay, looks like I use apps theta 1 for the first link, apps theta 2 for the second link. And so print apps theta 1, apps theta 2. So I intentionally wrote it in the init code, so I can only print it once. Let's see what it is. Okay, just print it once. So you can see it's 0. So for the leg one, which is perfectly aligned with the gravity direction, should be 0. And for leg 2, it's minus 0.43. Okay. Now our convention is that if it is pointing this way, or if you look at the vertical direction is straight up, then this angle is actually counterclockwise. So this should be positive and not negative, which means that I need to fix the angle here, the sign. So I go here and I actually change this to negative and negative. This is just saying that it's just making it the way I want the sign convention to be, which should be positive. So now if it prints, it will print 0 and 0.43, which is the angle or direction I want it. Okay, so that takes care of the absolute angle. So I'm done with getting the absolute angle of the leg. The final thing I need to do is get the position of the foot. Okay, and that will be needed because I need to know when the foot hits the ground, and that I can get pretty much from get object position from the API. So we take this, check the syntax of that. So syntax is, okay, so this will be over here, and actually I should have put it over here. So let me just take this and put it here. And anything, as I said, which is over here is going to be updated every single time this is called. So I want this to be called every single simulation time. So I put it here. I also want the gravity, the yaw angle, to be computed every simulation time. So I put that here. So this finds boom angle and sets gravity. Okay. This one gives absolute position of the legs. Okay, the last piece is position of the feet. Okay, so that's simply, let me call that position foot one. It's basically the sim.get object position foot one, and then we need to specify about which frame we want it. So that should be world frame. So and since foot one and foot two have not been defined, to go here and then define them. Foot one. Foot two. Okay, let's just print this. All I'm interested here is really the third component. So print position foot one, the third component, position foot two, the third component, which is Z component. Okay, so let's take this, let's just run this and stop it. Okay, now we can see the position of the foot. You can see that it actually is, so the left, the foot one, which is the leg which is on the ground, it's 0.025 or close to that, which means that it is on the ground. And the other one was 0.1 because it was at 25 degrees. And then as the foot basically hit the ground, both of them basically made contact. So you can see it right over here. 0.25, 0.025, 0.025. Okay, so that's good. So, so this just means that the code is working fine. The sensing code is working. So this is all I need for sensing. Okay, the final piece is the control. Okay, so let's just, before I go any further, let me just change the colors of the legs. This makes it easier to talk about them. So leg one, let's just make it, I think I chose green to be the color. So color. So I can just say it's the green leg. Okay, and then let's change the color to of the leg to the blue leg. And then just to make the feet visible when they contact in the ground, let's just change the foot to black. So the other one. Okay, now let's see all set. Okay, now, okay, next part. Okay, so now what I'm going to do is I'm pretty much going to use a finite state machine we've talked about in last class to develop the controller. Okay, now there's a hip and there are two ankles. So you would think that there are three state machines, one for the hip and two for the ankles. Well, I'm going to have a third state machine, and that state machine is only going to keep track of the stance foot. Okay, so these two are associated with the motors, right? The hip ankle. This one is associated with the foot. Okay, it's just going to keep track of which foot is on the ground. It's leg one or leg two. And this is the slide I fixed. So this is the state machine for the stance foot. So leg one is on the, let's say is on the ground. So that the state machine for the stance foot is equal to the one that says that leg one is touching the ground. So when leg two touches the ground, right, it just touched, this is when we will see that the foot two is on the ground, which can be determined by the position of the foot. And then we can also see that the leg two is in front, which means the absolute angle of leg two is positive. Okay, so that's the angle made by the leg two with the vertical measured in the counterclockwise direction, so it's positive. And so when both these conditions satisfied, you go to leg, you switch the state machine to leg two, which means now leg two will be on the, will be the stance foot. And then vice versa, when leg one is on the ground, you can have the same, similar to conditions for leg one. So that's my state machine for the foot. So the next state machine is for the hip. Here, what I do is I start the hip in the hold position, just at 25 degrees. And once it makes one step, I just switch the swing mode, which is basically put the hip spring and just keep running. So there's nothing going to happen interesting over there. It's just going to set the hip spring and it will just keep going. For the ankle, the state machine, there are two ankles. I'm just going to show it for one ankle, and then the same thing applies for the other one. So there is two states. One is stance one and retract one. That the one is for the corresponding foot. So foot one would have ones for it. The stance is when the ankle is fully extended, and that is when you want it to be in contact with the ground. It's retracted when it's swinging in the air. So let's say that the stance one is in the leg one is on the ground, okay, and it has been extended, so it's this distance 0.2. So when that's in that position and leg two makes contact with the ground, okay, that's when we want to retract the foot on leg one. Okay, so that's when you go from stance one to retract. I suspect that I made an error here, or maybe not. Stance foot equals 2. If stance foot is 2 and leg 1 is back, absolute leg 1 is negative, this is right, then I should go to retract. So the moment leg 2 touches the ground, I need to set the foot 1 to retract. That's all it's saying. Similarly, when the leg 1 swings and it's forward, I want that foot on leg 1 to be ready for stance, right? So I need it to go to stance phase. So I retract it when leg 1 is behind. I protract it when the leg 1 is in front. That's all I need to do. Okay, so let's see how to program this. Now, before I start programming this, remember that any state machine has to be initialized, and that's a choice I can make. For the hip, I actually chose the hip to be in a hold position. I need to make some decisions for the stance foot state machine, and in this case, I'm just going to assume the way it is set right now, which is, you can see that leg 1, which is the green leg, is on the ground, which means that leg 1 is the stance foot. So it's going to start in this. And then for the ankle, you can see that this should be in a hold position, or stance position also should be in a hold position. So ankle 1 as well as ankle 2 should be in the stance position. That's how I'm going to initialize. So let's just set that first and then worry about the transitions and state machines. So let's just do that in code. So open that. So let's start initialize the state machine. Okay. So before that, I need to decide the phases on the state machine. So this is how I'm going to call them. State hip hold equals 1. State hip swing equals 2. State ankle 1 retract equal to 1. State ankle 2 stance equals 2. Ankle 1. And these names are just to make it easier to code and nothing else. So ankle 2. I could put some states for the foot, but I'm just going to skip that. Okay, I just keep track of foot as I'm just going to keep the track of the foot state machine as a string, just to show you the variety. So I'm going to assume that. So I'll show you what I mean in a second. So now let's just initialize the state machine. So for the state hip, which is how are you initializing the hip state machine? Well, I'm going to initialize it with the hip hold. And then I'm going to initialize the ankle 1 with stance, since it's on the ground. And then I'm going to initialize the state ankle 2 also with the stance, because it's actually now forward and about to hit the ground. Okay. And then I need to initialize the stance foot hip machine. So state stance foot equals, and I'm just going to use a string for this. Okay, just for variety, but you don't need to do a string. You can use numbers like I have there. So leg 1 is the stance foot, because the green leg is on the ground. That's the stance foot. So now I initialize the state machine. I need to also initialize the controls within the state machine. So I need to set initialize the controls. I need to set what I'm going to do with the hip motor, what I'm going to do with the ankle motors. So let's do that one at a time. So let's start with the hip. The hip is in first of all in the torque mode. So let's set the hip in the torque mode. So for that, I'm going to again copy some of my code which I wrote earlier. This is the code which helps me to set this into torque mode or assign torques. Okay, so all it does is you tell it which joint you want to put in torque mode, and then you need to give the torque value. It basically puts the right max force and target velocity so that you can get positive torques and negative torques. And this is just, there's a video on how this is done in one of my earlier classes related to a pendulum. Okay, so I'm going to use this. Before I set it to torque mode, I also need to set to do motor enabled, and that I do by, and so if you show you what this means. It's basically if you go here and you go to dynamic properties, you need to do motor enabled. So that motor enabled is a command in CoppeliaSim, which I'm going to put next. It's basically, I'm just going to copy this from my notes. The command is that. So that basically takes the hip, it puts it in the motor enabled mode. The next thing I need to do is I need to set torque with the joint, which is hip, and then I need to give it a torque value. Now, what the torque value is? Well, now I know something about where this. I know something about this leg. The mass is 1 kilogram. It's at a distance of 0.4 from the hip. And since this leg is, well, it looks like what the angle is, since the other leg is vertical, so I can say that this angle is going to correspond to the hip angle, which is 25 degrees. And 25 degrees or 30 degrees for that matter is about 0.5. So what I'm going to do is I'm going to find the exact torque and put it there. So let's find the torque is mass times gravity times the center of mass times math dot sine of, in this case, it's 0.5. Okay, so let's write what m is. M is 1, G is, it's already here, so let me just copy it, just put the gravity here, that's better. And then C is, as I said, 0.4, and I think that should work out right. So if this is proper, then it should just hold on. Before I can run this, but let me just actually put the ankle, set the ankle motors, and that should be better than just running it right now. So let me set the ankles in position control mode, and this is again some of the things I've done earlier, in some of the earlier videos. I'm just going to copy paste that code from my notes. So this is setting the ankle 1 state machine. So 1, 1, 1. So what I'm going to do is I'm going to define an ankle stance position somewhere in my parameters. Maybe I should also copy this parameter over here. Okay, and maybe I can just make this also a parameter. Let's call this hip set point. So hip set point is 0.5. The ankle stance position is the same for both of them. And I remember, if you remember in the modeling phase, I chose that to be 0.2. It's fully extended. And then I can set an ankle retract position. And I'll set that to 0.05 because I saw that 0 actually makes that thing interfere with the leg. So I don't want that to happen to 0.05. So now this is also set. And this is a P gain I just chose. You can choose a higher value and see what happens. This makes the collision slightly soft, but if you increase it, then I think you get a hard collision, which we can play later on. Okay, so I'm going to copy this, paste it, and then change from ankle 1 to ankle 2. Okay, I think if everything looks good to me, we can at least do one step now. Okay, there's an error. One of the argument types is not correct in line 43. 43. Oh, I've not defined the ankles. So let's just do that. Ankle 1. Okay, now let's see what happens. Okay, that looks good. It actually took one step. Okay. Okay, so we got one step going. Now we just have to get the other pieces rolling. So let's just work on the second piece, which is now go to the actuation part and put some code here, which is basically two things, right? One is setting the actions or setting the transitions for FSM or finite state machine, and setting the actions for FSM. Okay, the second part is actually simpler. Let me work on the second part before I do the transitions. So what are the actions? Well, we have, if you remember, there are two states for the for the hip. And those states are, well, if the state hip equal to state hip hold, then what do you need to do with the control? You need to set the torque in this case. So in that case, we've seen that we need to set the torque, and it's basically this formula. That's all. Okay. If it's in the hip swing state, I need to set. Okay, what I need to do? I need to set the torque. So what's the torque due to a spring? Well, it's going to be K times sine of hip angle. Again, this should be a negative sign. Right? The torque due to a spring is minus K times sine hip angle, where K is the rotational torque constant, and that's something I need to tune. So torque is this. So let me just put that. So math it out. That the hip angle can be found because there is a command to get the hip angle position. Hip angle equals get sim dot get joint position hip. Okay, and then that will go here. So this K is something I need to tune. So let's just set that to 0 first, and then we can just keep ramping it up. So the way I like to do this is I like to, instead of making it some number which I create from scratch, I actually would like to make it some fraction of the existing gravitational torque. The existing gravitational torque is mass times gravity times c, right? This is the mgc. This is the torque due to gravity if there was no spring. So I can just tune this fraction. So let's just put 0 now, but we can keep ramping that up till we need to do whatever to get it to work. So that's that. So we've got this working, or rather have got this coded. Now let's move on to the next state machine. And now we have the ankle state machine. So that is if state ankle 1 equals state ankle 1 retract, then I just need to set the joint target position. Sim dot set joint target position, and the syntax is object handles ankle 1, and then the target position. So I've already set this up. It's going to be my set point, which is right here. Track position, stance position. Okay, so just put that. That's all. Okay, and then I need to have the state for ankle 1, which is stance, and then that position will be stance position. So, and then the best thing is that the state machine is the same for this command is the same for ankle 2. So that takes care of all the controls. Now we only need to work on the transition. Okay, and let's see how to work on the transition. So let's start with the foot first. The four state machines are the foot state machine, hip state machine, ankle state machines. There are two. It turns out that if you can program one ankle state machine, the other one is pretty simple, just the same thing, copy pasted. So we're just going to work on 3. Okay, so let's work on the state machine for the foot, right? This one. State stance foot. So we need to keep track of the switching between them. Let's go here. Okay, so what's going on here is we want to keep track of the switching, and the best way I think of keeping track of the switching is if leg 2 is on the ground, and if the foot on leg 1 reaches that critical value 0.025, then I know that we can transition. So what I'm going to say is here, if state stance foot equal to leg 1. Okay, so that means that leg 1 is on the ground. Okay, if leg 1 is on the ground and I'm trying to detect when leg 2 would hit the ground, then I need to check that the position of foot 2, right? Because leg 1 is on the ground and I'm trying to see when the leg 2 or foot 2 is going to hit the ground. So foot 2, the third coordinate is less than equal to, you can put 0.026 if you like, because 0.025 was the critical value, or you can put 0.025. Let's see what happens and we can change it. Okay, so in that case, what I need to do is I need to switch the legs. So stance state, stance foot equal to leg 2. So switching goes there. And then if you like, in this print, switching from, or just forget it. This is keep track of the steps. Increase the steps. I need to keep initialize the steps. The step is say 0, and then if that foot hits the ground, the step is increased by 1, and then let me just print this because I want to keep track of the step number. And then end. Okay, so that is the state machine for stance foot. Now this is just one piece of the two transitions. So once I'm in this state, I need to go back to leg 1. So that will be just replacing this 2 with 1. So this will be 1. Now this is when the leg 2 is on the ground. I'm trying to detect when leg 1 hits the ground, and that will be when the Z position of the foot 1 is at the critical distance, increment, and then that's all fine. So that completes another state machine. Next, we'll go on the transition for the hip state machine. So let's open that. Okay, now this one is going to be in hold in the start. And then after one step, I need to trigger to swing. So the only thing I need to check is, has the step been incremented from 0 to 1? Then I make the switch. So for the hip state machine, I say if the step is greater than 0 and state hip equal to state hip hold, then I say that the state hip should go to state hip swing. Okay, so that's all, and there's nothing more to happen in here. Now let's go to the ankle state machines. Now for the ankles, let's just start with 1, and then the second one is pretty simple. It's just a switching of the appropriate ankles. Okay, so let's see the ankle 1 state machine. There are two things going on. One is we need to be moving from stance to retract and back. Okay, so where are we actually starting this robot from? Let's see. We are starting the robot such that ankle 1 or foot 1 is, well, leg 1 is the stance foot. It's in the stance position. Okay, so let's see. So it is basically here. It's in the stance position, and this one is going to hit the ground. When the foot 2 hits the ground, we want the back leg to retract, right? The moment this hits the ground, it becomes a stance leg, and leg 1, which is the green leg, is to now retract. Okay, and the retraction in this case is, so we want to basically figure out how to go from stance 1 to retract 1. So let's just look at what I wrote here. Seems to have lost the slideshow. Where is? Okay, so the leg 1 is in stance, and leg 2 just hit the ground. The blue one's hitting the ground. When stance foot 2 is when leg 2 becomes a stance foot, so we check the leg stance machine or the stance foot state machine, and we also ensure that the leg 1 is behind. Okay, and that is only done as a safety measure. Okay, because that way we can be. So it's always good to put redundancy. I'm pretty sure that if you just use this one, it'll work. And we can actually try removing it out and seeing if that works. So let's just do that and see if that works. I'm just going to use 1 item here. Only going to check if the leg 2 is on the ground and ignore the other one. So if I ignore the other one, then I just say that if state ankle 1 equal to state ankle 1, in this case was stance 1, then so and okay, so when it is stance, when the ankle is in stance, leg 1 is the stance foot, right? And so in this case, I need to check if the stance foot, state stance foot equals leg 2. Okay, so this is when the leg 2 has hit the ground, and that's when I want to transition. So then state ankle 1 equals state ankle 1 retract. Okay, that's one. The second one is the second one is when the leg 2 is on the ground and leg 1 is in front. Now here I cannot avoid. I have to set the condition that absolute leg 1 is positive, because only when it's in front, that's when I want to transition. So that 0.05 is randomly chosen, so it's just in front. You could also choose it to be 0 or 0.1. I'm just going to stick with 0.05. So stance foot is on the ground and leg 1 is in front, which basically is that, say it's 0.05. That's the condition. So again here, if state ankle 1 equal to state ankle retract, so it's in the retract state, and apps, so I need to go look at the angle. So track apps θ1. So this should be theta. So if the ankle 1 is in retract, and I need to check θ1 is greater than 0.05, and perhaps I need to check. I'm just seeing if I can avoid this. I think I can just avoid this. If not, I'll come back. Okay. And then I can just say okay, so this is to be copied again for the other ankle. What? So hope I did everything right. See what goes on here. There's an error. 70. Okay, 70, there's a problem. So at 70, it tried to get something, it did fail. And so that was position foot. Okay, the problem here is that the way this code works is init is called. After init is called, the first thing we just called is actuation. Okay, but our initialization for these things are done in sensing. So sensing is not called before actuation. So I need to call this sensing in the initialization. So that way it's called, all these things are updated, and then it goes to actuation. So I'll just call that once inside here. I hope it'll work now. Okay, there's another error. One of the argument type is incorrect, set joint target position. So let's see 124. 124. Set, haven't I set this? See if this is, maybe I did not. Oh, this is spelling error. Okay. See if that works. Okay, so you can notice that it actually did not retract in place. You have to place. And then you can also see the steps numbers are increasing so fast. There's some problem here. So I suspect that is because I ignored some of these conditions. So stance foot, I ignored the fact that, so it's basically going here. It just keeps updating the step numbers when it should have only done that once. It's very difficult to play this slowly. Stop. That's step number 1. That looks right. Okay, when it falls, all bets off. There's something about, I think that it's the retraction is not triggered, and that causes a problem. And once it falls, it just keeps incrementing random. So that's step 1. Step 2 is correct because now it hits the floor, but it did not retract. That's the problem. So we have to look at the code where it failed to retract. In fact, ankle 1 failed to retract. The walker I developed in the class last time, and when I run this, it falls. And then the steps keep increasing. Okay, so what's going wrong? Well, what I'm going to do is basically debug this. And what will help me to debug is actually using what is known as the pause. So if you go to CoppeliaSim and let's see. So you can pause the simulation wherever you want. So pause simulation. The syntax for that is it. And so here, when I want to pause it, is exactly when it takes a step. It seems like something weird is going on. So I'm going to put it here. So the moment it takes the step, it basically pauses. So now it will go, it'll pause. Now we expect this back leg to retract and doesn't retract. That's why it doesn't clear the ground. It stops the floor. So there's something wrong with the leg. So this is leg 1. So ankle 1 of which is associated with leg 1. So let's look at the code. So we are trying to retract. So we have to go from stance to retract. So the state ankle 1 is stance, it goes to retract. This is what we're checking. It turns out that I had made an error with this state machine itself. My state machines the states are not defined this way. So if you go here, and you look here, this is how the state machines are defined. I'm just going to copy this so that you can compare. This looks so right, but it's so wrong. So it's state ankle 1 retract. It's not ankle 1 stance 1. It's unfortunate that CoppeliaSim actually doesn't give me an error that this variable is not defined. Anyway, so I'm going to get rid of this one, and then that one, and then this one, this one. And I think there's an error here. See, this ankle should be ankle 1. Okay. And then I made the same error for this. This should be, this 2 shouldn't be here. This 2 should actually be here, here. And then I missed one here, 2. Okay, so I think that is fixed unless there's some other error. Looks fine. Okay, now let's see what goes on. Okay, it lifted, which is good news. Next, it fell down. Okay, so one thing I want to tell here is that one of the problems is with the simulation. You simply don't want to go 50 ms, which is not so accurate when it comes to putting a spring. And for such simulations, I would just change that to 10 ms. Okay, so let's make that change, let's save it and run it. First step. So you see that's totally different now. It's actually the blue leg is behind when you do at 10 ms, but if you do 50 ms, it's front. So I can just compare it. So look at, remember this snapshot where the blue leg is sort of behind the vertical line. And now if you do 50 ms and run it, you can see it's so to say it's in front. And that's because of the spring between the two. In this case, not the spring, it's basically the hold position which is causing that. Okay, so let's do this and then run again. Okay, so now there's another problem, which is it doesn't quite go to stance. It doesn't quite put the leg out there, right? It should be stretched. The leg should be stretched. So let's see what's going on here. Okay, so let's see if you can find something. It seems like the problem is when ankle one goes from retract to stance. So ankle one going from retract to stance. This is where the problem is. This looks right to me. I fix this. So when it's retract to stance, the leg one is the one which is going in front, and that angle should be positive. That's fine. There's no problem there. Maybe it doesn't quite go to 0.05. And okay, so I found one other error here. The torque should be minus k times sine. This sort of acts like a restoring force should be minus, not positive. Let's see if that fixes it. So maybe it was not swinging further ahead. Okay, next step. Okay, that looks better. So it was the hip spring which was the problem. Okay, I can keep going. Okay, that's good. Keep going. Okay, it looks like it fall. Okay, now it's dragging its foot. It's all steps. Okay, it's went bad. So this is a more subtle one. It turns out that I had not fixed something in my model. So my model assumes that the mass of the leg is 1 and the center of mass is at 0.4 from the hip joint. Now, the hip joint is here. So I need to ensure the leg mass is actually 1. It turns out that I had thought I'd fixed it, but I actually did not fix it in my model. So this is 1.1571. I could change that in the simulation, the code, or I could change this. Either of those two will work. So let's put 1 here. And then let's put that also equal to the first one. 1. Okay, and let's hope that fixes it. Okay, this pause, I'm going to remove the pause. It's just going to make me do this again and again. So let's just comment it out. Okay, that looks fine. Okay. Like it did one half circle or 3/4 circle. Okay, so that looks like it's going to go forever. Okay, so we can do a few things here. First of all, if you notice the, the position control is here is rather weak. So when you go do this, you can see that it's actually hitting the ground and compressing. So I can actually change that gain. So it's set to 0.1. I don't know what happened if you put 1. Maybe it will not work. Let's see. That's a firmer foot strike. Okay, that looks, it works fine. Okay, let me just zoom it this way. Okay, let me just change that to ramp it up. So that's maybe 5. I think the P control here makes it act like a spring, but this one also has no problem with it. I think it still has that softness to it. because there's still softness. I think I can change that by setting the D control. So I don't know if it's going to work now. Let's see, let's just try 1 and 0.1. So it's damping out, so it's going to resist doing the springy motion. It's going to damp out the springy motion. Okay, let's see if that visually change anything. It still is doing that. I mean, I'm not opposed to that. That's fine. It's not that it's not working, but I just wanted to see if that's changing this gains. We'll have, oh, my bad, I'm changing the I gain. I should change the D gain. Let's try the D gain now. Okay, yeah, that was bad. So the damping didn't help. Let's try 0.1, which is a lot less, but it sort of prevents it from the collision. Yeah, I think that has no effect. It looks the same. So let's ramp it up to 0.05. Okay, so it fell down. Okay, so this is very sensitive to that parameter. So that's something which is important, which is I would highly recommend that you want to do this parameter studies on whatever you do, because when you do things on hardware, if things fail in software, they're definitely going to fail in hardware. So you do the robustness study just to understand what parameters this gate is sensitive to. Other thing we can try to do here is I chose a spring constant. In this case, the spring constant was about 2 times the gravitational torque. I could change that to 3. Let's see what happens. So it fell down because it just went too fast. We can actually let me rotate the view. This is good enough. Slight rotation. Okay. So if you want to change the spring constant, you might as well change the slope so that it has it can actually so changing the slope might help, because now you're giving the hip or the stance leg more speed because it's going down at more steeper ramp. Okay. That seems a little bit too much. Let's try 0.15 instead of 0.2. Okay, so what's happening here is it looks like it's working well. So the moment you increase the ramp slope, what happens is the leg needs to swing much faster. And that's what we did by increasing the spring constant. That way it has more, it can swing the leg much faster to break its fall. Okay, that looks good. Now, what happens in this case is when it falls down, the simulation keeps running, and so the steps keep increasing. In real life, you have an e-stop, right? You stop the robot using an e-stop. What you can do here is you can actually have like another state machine, and I would highly recommend doing this. I've not done this here, but you can totally do it. You can have a state machine which basically keeps track of failure, right? So for example, some conditions to check is the swing leg angle too much? Say it goes to say 60 degrees. Okay, 60 degrees is a little bit too much. 30 degrees or 45 degrees is what you see. So if it goes 60 degrees, you can say either pause simulation or you can do stop simulation. The other command is stop simulation. If the hip height or the center of mass, the hinge joint, for example, if it penetrates the ground, it's fallen down and you want to stop the robot, so you could use that condition. So you can do a bunch of cases you could check, and that those cases basically help you to kill the simulation. And the reason why you want that is in real life, when you actually program the robot, you are really concerned about the robot falling down. So you always want to have those conditions in there, checking things up, okay? And it may be, it's one thing to write a successful walking controller, but it's equally important, or perhaps more important, to actually have or list all the cases in which the robot would fall, in which case you want the controller to stop, right? For example, let's say that the robot fell down and your controller is still applying a torque on the hip. Now something nasty will happen to the robot, and it will actually make perhaps damage the motors, and that means that you have to spend a lot of time fixing the robot. So you clearly need to have those cases, which I don't have in simulation. But when you program this in simulation, please think of all the cases the robot fall and have those conditions inside to kill the simulation, and that will be a good programming practice. The reason why I have a hip spring in this case is because when the way this works is, this is a passive robot, so it walks downhill, and the way I simulated downhill is in gravity. It turns out that the natural inertia of the leg, which gives it a certain time period, is not good enough for it to swing its leg fast enough so that it can break the fall. And I need to tune the frequency of the swing leg depending on the slope so that it can take that step. So for each slope, there is a spring constant which enables me to make this robot walk successfully. So as I increase the slope, you will expect that the robot walks faster and faster, which means that it needs to swing its leg faster and faster. And the way I make the leg swing faster is by increasing the spring constant. So that's how we saw that there's a spring constant. Okay, now I did this simulation in Matlab, and for Matlab, I did not have a spring constant. You could try that. You could decrease the slope to. So what will happen is, for 0.1, we saw that the spring constant was 2, right? And that it worked fine. You could try to arrive at the solution where you require almost no spring, hip spring. So we can try to see if we get that solution. So let's just decrease it to 0.05. Let's change spring constant to mgc and see what happens. So you can see it's working much slower, but it's able to do it with half the spring constant. Now the slope has decreased. Okay, so this works. Let's further ramp it down to, I think, let's make it 0.25, and let's just make this 0.5 of all this. And I don't know if this works. Let's see. Okay, so that's kind of impressive that it works. It takes short steps, though, as you can see. Okay, now let's just try to go even down. Let's put 0.1, and then just change this to 0.0, 0.2, so 0.1. Let's see if this works. I need to ramp up the spring constant. As you can see, it didn't really swing its leg fast enough. So maybe 0.2. Yeah, it's going to work. Decrease the slope, maybe 5. Nope. Okay, so there's another problem, which is I have these conditions which I also need to tune. Like I assume that 0.05 is good enough for the leg to protract or go in the stance state. I might tune this to 0. Let's see if it works. Because I'm doing this by really guessing, but really the way to do this is to actually to look at the animation and simulation and then do accordingly. Let's see if this works. Nah, this didn't work. So it's really there's a problem going down, decreasing the spring constant. So point. Oh, I'll change this. My bad. I should have changed this one to 0. Okay, let's try this. See if it works better. No. 0, 5, 0, 5. Let's get back to 2, and then scope is 1, and I think so. Okay, so any questions? Okay, so no questions then. Let's stop.